Okay, this is the second half of the top three things in each chapter here. I'm going to continue on. We're going to do chapter 16, 15, and 14, but we'll see how those go. And let's see, where's chapter 16? There's chapter 15. There's chapter 16. All right. So let me go ahead and share my screen. Let's see if it's going. The video's up here. And let's go ahead and put the chat there. All right. Oh, you think we're on 17? Wasn't 17 our aldehydes, our enolates and stuff? 17. Nope. Yeah, the reactions at alpha carbons. That was, oh, that's 18. That's 19. That's 16. 17, carboxylic acid derivatives. There we go. Okay, I'm gonna have to do it this, nope. All right, 17, carboxylic acid derivatives. Okay, these are, the key here is functional group transformation and the fact that we have a new leaving group. And when we had aldehydes and ketones, we had addition reactions because once you added something across the carbonyl, we didn't have a good leaving group. However, in the case of the carboxylic acid and carboxylic acid derivatives, we now have a good leaving group so we can regenerate the alkyl group. So that's why we get a lot of substitution reactions on, substitution reactions on carboxylic acid derivatives, where we don't get that on.
Hello?
There we go. I muted somebody. So, okay, anyway, so we got there. All right, so the key here is functional group transformation. How do we get to the carboxylic acids? Through oxidation. And then how do we change those different groups from different places? And we have different reagents for that. And the thing to remember is that we go from the most reactive substrates down to the least reactive substrates. For example, acid chlorides are the most reactive. So we can make all the other functional groups out of an acid chloride. Carboxylic acid and esters are about the same, and so we can make those out of anhydrides and acid chlorides. But once we get to the amide, that's the least reactive of the set, and so we actually have to hydrolyze off that amide to get it to go and make an ester or a carboxylic acid. So the reactivity series is a key phrase in these things. And converting from one to the other using different reactions, okay? So in the general scheme of things, the entire set is set like this, where we have going from most reactive down to least reactive in order, is the acid chloride, the anhydride, the ester and carboxylic acid are about the same. A nitrile is just a dehydrated amide, but it actually has a triple bond there, so it's slightly more reactive. And then the amides are the least reactive of the set. And they, of course, are classified by how many carbons are bonded to the nitrogen. Okay, so knowing that they each have names and knowing that you can interconvert from the others is the key phrase here. Knowing that we have how to name them and that the diacids have common names. And I like this acronym, or sorry, this mnemonic for remembering the multiple carbon systems, where we have a 2-carbon is oxalic, malonic, succinic, butyric, and diptych, with the OMI, such good apple. And then the carboxylic acid, the dicarboxylic acid phenyl rings start with phthalic. And then we have isophthalic and terephthalic. So knowing those common names will be, is also important. Knowing how to name the esters, the amides, Carboxylic acids are carboxylic acid. Acid chlorides are the acid, acetyl chloride. Knowing how to name them systematically is important. The esters have 8, but you have to also include whatever alcohol you made them out of. So it would be like ethyl acetate, etc. So that's nomenclature on the system. And this is a summary of the nomenclature right here. We have those. And notice on the nomenclature set that carboxylic acid and carboxylic acid derivatives have the highest priority. If you have a carboxylic acid on any part of your molecule, you're naming it for that carboxylic acid, okay? And then, of course, it goes down to, amides and nitriles and stuff like that. All of the carboxylic acids are the highest priority set we're going to look at, okay? So then once we, oh, no, we're not going to do spectroscopy. There's no spectroscopy on the final, sorry. The next thing is how to make them. And we've borrowed some stuff from previous chapters like potassium permanganate or chromate, but we've also added one that we may have not looked at before, which was ozone. Ozone, you can actually oxidize benzene rings off, or you can oxidize carbon-carbon double bonds to generate your carboxylic acids. So that's one of the key ones there. So in the case of, you have a benzene and has benzylic hydrogens on it, and you use permanganate, you end up making the benzene carboxylic acid. If you use ozone, you actually end up oxidizing the benzene off and making an aliphatic carboxylic acid. So this is kind of an interesting way of selectively choosing your reagent to get the product you want. Okay, and then of course, you can usually oxidize anything down with permanganate or with chromic acid to generate your carboxylic acid. However, aldehydes can also use a milder oxidizing agent. And this is that silver Tollens test, or the silver test. We learned about that in also chapter 12, but any of these oxidants will take us up to carboxylic acids. Once we have our carboxylic acids, we can also make them with Grignard reagents by insertion of CO2. Once we have those carboxylic acids, we can then interconvert them to other functional groups from the carboxylic acid as well. And these are just addition reactions. Okay, let's move on to right here. Okay, so this is the most reactive. We make acid chlorides specifically with 2 reagents we use. The primary reagent is thionyl chloride. SOCl2 is the #1 way to make it. However, you can also make it with phosphorus trichloride or phosphorus pentochloride. Okay, and the whole idea is that you're making an OH a better leaving group and generating that very reactive acid chloride. Once you have your acid chloride, that's actually a great substrate for making your acid anhydrides, which you have to do by reacting your acid chloride with a salt of carboxylic acid, and that'll generate your acid anhydride. Then you could also react it with an alcohol or an amine to generate your ester or amides. Okay, so it is the most reactive. You can make every other functional group from it. So that is the key phrase about those. Once you get to the less reactive substrate of the anhydride, your anhydride can be used to create esters and amides, but it cannot be used to generate acid chlorides. Okay, so it's the next most reactive. So you can get to esters and carboxylic acids and amides from there. Okay, now once you get down to the esters, now we have to look at a different mechanism for how these react. In these first 2 right here, where we have the acid chloride and there, all we have is nucleophilic attack at the carbonyl and then the leaving of a very good base. Okay, once we start reacting esters, we're starting to look at a different reaction, and that's like a trans-esterification reaction or a trans-amination reaction. And that's here. So in the case of the esters right here, we can interconvert from two esters by just using acid and an excess of the other material, okay? So the first way to make an ester is just to take your carboxylic acid, a little bit of, a lot of your alcohol, a little bit of acid, and you drive water off, okay? So just making the ester is called the esterification. However, you can convert one ester from the other using the ester trans-esterification, okay? And that's where you put a whole bunch more of another alcohol in there and hopefully boil off the lower molecular weight, okay? Once you have your ester, you can also convert it into your amide by displacing your alcohol with an amine, because the amine is the stronger base, and it'll displace that to make your amides. Oh, that's up here, sorry. So if you react any amine with a acidic hydrogen, you can get it to displace to make a primary, secondary, or tertiary amide. Okay. And then the last ester reaction we have is the hydrolysis. And we can do it by acid or base means. However, the acid-base system is catalyzed because you regenerate your acid in the last step. The base system is promoted because you're ending up deprotonating the carboxylic acid you just made, and therefore your base is consumed in the reaction, okay? So base is consumed in the hydrolysis, acid is regenerated in the hydrolysis. That's the key step on this, on the hydrolysis of esters. And that takes us up to the last set, which is the amides and the nitriles. So I showed you how to make the amides directly from esters. You can make them from acids, acid chlorides, esters, or anhydrides, and you just have to use the correct number of equivalents of the system, because in a lot of them you'll generate a base. So a lot of times you have to use two equivalents of the base, of the amine, to get it to go to reaction, okay? You can also do a thermal dehydration once you create the salt to actually generate your amide as well. We didn't use this reagent very much, but I wouldn't worry about it for this particular exam. So again, it can be made from any of the other systems. Then once you have your amide, if you have a primary amide, you can do a very interesting thing where you can take away an equivalent of water and turn it into the nitrile, okay? So in the bottom half here, it shows us using a P4O10, also known as phosphorus pentoxide. And what it does is it takes out 2 protons from the amine and 1 oxygen from the carbonyl compound and generates your nitrile. However, in chapter 7, we learned that we can also make nitriles by using the nitrile as a nucleophile and displacing a halide. So those are the 2 primary ways we make nitriles. Now, nitriles can be hydrolyzed with acid or base, and then they'll go back to our carboxylic acids or our carboxylic acid salt. Okay, so the key thing here is that we can go, once we have a carboxylic acid, we can go back and forth between all the derivatives if we know how to do it. If we get, as we get to more and more stable, more and more amides, we have to go and hydrolyze them down to carboxylic acids to get them to go back up to everything else. And as we learned in the amine chapter, we can reduce down our nitriles to generate either a primary amine, or if we use dibol, we can actually stop at that aldehyde as well. Okay, so that's chapter 17, carboxylic acid derivatives. And so we learned how to make them through oxidation, convert them with the various reagents to one versus the other. And let's see, trans-esterification I said, okay. All right, so that takes us through the top chapter 17. Chapter 16 is all about aldehydes and ketone preparation from other locations, okay? So if we look at the aldehydes and ketones, we're gonna do nucleophilic addition at that carbonyl carbon. Okay, so obviously we have nomenclature to start with. No, that's not what we do. Where is it? Chapter 16, yeah, there we go. Okay, so we have nomenclature for aldehydes and ketones. Then how to prepare it. We have selective ways of going from aldehydes to ketones. If we have our primary alcohol, we only have one reagent that'll give us a direct oxidation, and that's PCC, okay? However, if we have an alkene with a hydrogen on it, we can use the ozone oxidation of the alkene to generate our aldehydes. If there is no hydrogen on the alkene, we actually end up generating a ketone. Right. So we can also do a selective reduction, okay? We can actually take a carboxylic acid derivative and convert it into an aldehyde by using a selective reducing agent. It has to be an acid halide, and it has to be a selective reducing agent, which is the lithium aluminum tri-T-butoxide. Okay, in this case, if we have the lithium aluminum hydride, we actually go all the way past the aldehyde or ketone to the primary alcohol. So we have two selective reagents we added in this chapter. One is the T-butoxy, the tri-T-butoxy material. And again, that does a selective one where we take an acid chloride to an aldehyde. And then we also have what we call dibol or dibol H, which is the isobutyl system. Okay. Now, one does acid chlorides and the other does esters and nitriles, and it takes them up to the aldehydes. Okay. So yeah, those are the two there. So ketones are actually easier to stop at if you have any ketone, any alcohol, a secondary alcohol. You can just use any number of oxidizing reagents and oxidize it to the ketone. So if you have a di-substituted alkene on one side, you can generate ketones from that. You can also generate ketones through Friedel-Crafts acylation, and you can generate ketones through oxidation. Now, PCC will oxidize a secondary ketone down to, a secondary alcohol down to a ketone, but a stronger oxidizer can be used as well, like the chromic acid or even permanganate can be used. Okay. So we actually also looked at making ketones by using a Grignard reagent, and you can do that by reacting a nitrile. And so this is kind of an addition reaction, and then it kind of stops at that compound with the nitrogen double bonded to it until you hydrolyze it. So it doesn't actually do a second addition, it'll just do a one addition, and then once you hydrolyze it, you will generate your ketone from that system. But the most common way to get to your ketones is through the oxidation process. Okay. Now, once you have your ketones, you get to think about their reactivity. Aldehydes are more reactive than ketones because of sterics. Okay, you have a small thing available to it, and therefore you have more effect on there. And then there's a secondary effect of your electronics. So the next thing we learned about aldehydes and ketones is how to protect them. Okay, you can selectively protect an aldehyde and ketone using the form of an acetal or a hemiacetal. And when you do that, it takes the carbonyl character out of that aldehyde or ketone and lets you reduce down other components. In this particular example, we made our acetal out of our ketone, and then we were able to reduce down an ester down to the alcohol and then regenerate that carbonyl compound. And let's not forget how to make our acetals. with using, oh, that's the big, sorry, using our alcohol and an acid or base catalyst to make our acetal. And using the cyclic acetals is the most stable and easiest way to go. So you use ethylene glycol to make that cyclic 5-membered ring is one of the best ways to protect an aldehyde or a ketone. Then of course we can do any kind of, yeah, and the Wittig reaction, that's actually an important one. We can take any aldehyde or ketone and turn it into an alkene with the use of our phosphorus reagent, our Wittig reaction. So wherever the ketone was, you now generate your double bond. Okay, so that's 16. The last two chapters I want to talk about are 14 and 15. 14 is all about what aromaticity is, okay? And of course, aromaticity must follow those 4 rules. You know, number of electrons must have pi, they all must be in a ring. They must have the right number of electrons, they must have p's, they must have in a ring, and they must overlap completely. So, and again, it has to follow the rules of being planar there and have the right number of electrons. That doesn't mean you can't have charge. So there's a lot of aromatic compounds that are negatively charged or positively charged, but they still follow all the rules of cyclic p orbitals, planar, and having an odd number of pairs of electrons, or follow the 4n+2 rule. Anti-aromatic is an even number, and if it doesn't meet any of those, it's not aromatic at all. So that's the rules of aromaticity up here. And in chapter 15, we talk about benzene specifically. And of course, we introduce a new mechanism here, and it's great because it's the same mechanism for all of our reactions here. It is a electrophilic substitution reaction with 3 steps. You generate something with a positive charge, usually with a Lewis acid catalyst. You have attack by the benzene onto that positive charge, and then you spit out a hydrogen, okay? Depending on which reagent you use, you'll end up with a bromine or a chlorine, or an acyl group, an alkyl group, a nitro or a sulfur compound, but it's all the same mechanism. We did do a reduction in this chapter, the Birch reduction. However, it's not very common. We don't typically use it. Okay, that's 14 and 15. Obviously, there's a lot of this individual reactions to remember in the Lewis acid acid catalyst for each of those reactions, but it all follows the same mechanism, and so those are very good. Oh, I forgot. Ortho, para direction, and meta direction, and activators and deactivators. That's key on the benzene reactions right here. And the best thing to think about there is if it donates electrons, it's going to be an activator and an orthopara director. If it withdraws electrons, it's going to be a meta director and a deactivator. I have, yeah, this table here. Knowing this kind of activation, deactivation is very important. The other thing to remember is if you have an activator and a deactivator, the activator takes precedent. It's going to direct where things go, okay? Because it's activating that site. So the deactivator, well, it's decreasing it and trying to direct it one location. The activator always takes precedent when directing your reaction. Okay, I think that with yesterday's covers all of our chapters. We did 12 and 13 and 14 yesterday, and we've done all of them up to now today. Do we want to do the top 5 things? Oh, hand raised. Yes.
For chapter 14, do we need to know naming of any of the heterocycles?
For the top ones like pyridine and parole, yes. There's 4 of them that I think I circled when we went through this during the winter.
Okay.
Let's see, that would be under this one. It would be pyridine. You have to know the special names for the monosubstituted benzenes, of course. And I think the only heterocycles we talked about were parole and pyridine.
Okay. Okay, great. Thank you.
Yeah, and that's cyclopentadiene. Yeah, it's parole and pyridine. Yeah, here we go. Parole and pyridine are the 2 heterocycles we need to know.
Perfect. Okay, thank you.
Okay. All right, so that covers the top things on each of those chapters. So alcohols, oxidation reduction, selectivity. Conjugated systems, we have 1,2 addition, 1,4 addition, and what controls the other things. And then we also have that Diels-Alder reaction to deal with in that chapter. 14, what makes something aromatic and which electrons contribute is important. And their names, the reactions, luckily it's all the same mechanism. So chapter 15, you just need to remember your reagents and the direction effects. Ortho-para director or meta director, activator, deactivator. That's a key thing there. Aldehydes and ketones, selectivity and oxidation and reduction. Carboxylic acids, how to make them, and the different reactions they do, and how to convert from one kind of carboxylic acid to the other. So from an ester to an amide to a carboxylic acid, how to convert back and forth. Alpha hydrogens, knowing which are most acidic and how to make them, how to then use those to do different reactions. And they have different names based on whether you have an ester, an aldehyde, or a ketone. And then we have the reactions of conjugated carbonyl compounds, and those have different reactions. When we get into amines, it's all about basicity and knowing how to make selective primary, secondary, and tertiary amines. And then in our last chapter, names of the reactions and what kind of metals are used in them. Okay, now we're going to open up for questions in any specific chapters you might have, and we will, I'll answer questions up until 1:40. Go to open blank page, and I can just.
I had a quick question. Sorry, on chapter 13, for the Diels-Alders, is there like a quick run through for endo versus exo?
Oh yeah, let me do that. Okay, first of all, the key things on your Diels-Alder reaction is you always have a conjugated diene and then something looking for a conjugated diene. So you have your dienophile, right? So on your, when you do this, you want to have your diene in that position right here. And to get endo versus exo is the idea that you are going to you're going to electrostatically kind of line these guys up before the reaction happens. And you electrostatically line them up before the reaction happens because it happens all at once. There's no moving once it happens. So, for example, if we do something like this, and this is our electron donating group, okay, that means it's going to have a partially negative charge on it, right? Because it's donating electrons to the diene. And we typically see electron donating groups on a diene. Okay. Now the dienophile, remember, is activated by having electron withdrawing groups on it. So if we have our electron withdrawing group on it, right here, all of our electron withdrawing groups tend to be partially positive. Okay. So what we'll see is we'll start to see the electrostatic partially positive side of the one compound start associating with the electropositive side, electronegative side of the other compound. And so what we'll end up seeing is that this electron withdrawing group is going to shift closer to the electron donating group when it's starting to get itself close. And so what we'll see here is that the electron withdrawing group, I'm just going to put a big partially positive here, is going to be kind of getting really close to this partially negative here. And so what we'll see is that when our bonds form, when these electrons kick in here and these electrons kick out here and these electrons kick out here, we'll see that our electropositive group is going to be down or indo closest to the newly formed double bond because it was electrostatically attracted to this partially positive group. I'm sorry, partially negative group. So the idea here is, let me just redraw this right here. Okay, so our diene is here, and I'm going to put a negative group here. So it's not really fully negative, it's just partially negative. Okay, and I'm going to put our dienophile here. And so it can come up and it can have its partially charged here. And that's okay, but there's nothing really keeping it there to have it react, right? And if we put our partially positive, we move that charge and it comes in, and in the next thing, it's like this. Well, there's nothing really keeping it there in that position, right? But if we, instead of having that group over there, that positive charge, had that positive, partially positive charge aligning with this partially negative charge, then when our electrons move, it stays there longer and allows our electrons to kick in like this. And let's not forget our hydrogens out here. And when we do that, if we look at our final product here, we'll see that that partially positive charge is going to end up down here. Our partially negative charge is going to end up here. And we'll just have our hydrogens here. So this pre-association of those charges drives endo to be the more favored product in the Diels-Alder reaction. Does that answer your question?
Yeah, it does. Thank you for kind of like color coding it.
Yeah. So yeah, it's all, you know, the Diels-Alder is hard because of you're literally, you know, stacking one on top of the other and trying to figure out how they electrostatically hold together in that, you know, before it even gets to that concerted reaction, because it doesn't have a transition state. It just has the, if I'm here long enough, my electrons move. And so you're trying to figure out the stablest position to put them in to get the electrons to move.
Okay, and this is probably gonna be like the dumbest question. And this is like a 7, is the endo and the exo always make like a 7 carbon, like, or like silic type like chair thing?
No, I've drawn it like this because I just wanted to show where the electrons kind of move to give it. We always get a 6-membered ring out of our Diels-Alder reaction.
Okay, gotcha.
You always get a 6-membered ring out of a Diels-Alder reaction. And there's always at least one double bond in the Diels-Alder reaction at the end. And it's always in between where the diene bonds were.
Okay, yeah, gotcha. Thank you.
Okay. All right, anybody else have a question? Okay, a little advice on attacking questions. Start with what you know. Okay, if it's a carbonyl, you got a partially positive side, a partially negative side. Attack it from that position. If you're doing a multi-step synthesis, okay, and you're given multiple steps, write the first product down, and then write the second product down, and then write the third product down until you're done, okay? Don't, if you don't write down the intermediates, you might skip a step. And so it's important to write each of them down. You get plenty of paper, you know, like 5 sheets of blank paper to do your exam. Write each step down, and then you'll be able to, you know, make sure you haven't skipped a step, okay? In nomenclature, use your nomenclature rules in order, okay? Start with your highest priority group, and then longest chain, and then substituents, lowest number, you know, boom, hit them all in order, okay? Benzene nomenclature is only slightly different because you're trying to get orthometapara. Let's see, what other attack reasons. When you're studying, make sure that you can, if you, like, let's say you have a ketone, okay? Okay, you can do addition reactions on ketones. You can do substitution reactions on esters and carboxylic acids. You can do substitution reactions on benzenes. You know, note it, you know, whether it's an addition reaction or an oxidation or reduction, you know, those little classifications as you go through your reagents, like these are always reducing agents. Most reducing agents are transferring a hydrogen negative, a hydride, okay? These are oxidizing agents. They tend to pull things off. Reagents that have phosphorus in it tend to pull oxygens away from systems. So look for these common themes with your reagents as you're going through and building your tables and your interrelational database. All right, other questions? We've got a few minutes here.
I had one more, and it was a homework question. I didn't know if we could ask homework questions.
Sure.
It's for homework 1, and it was, I don't know if you can bring it up, but it's for it's chapter 13. I just didn't, honestly, I just don't know how to attack this one or like where to start for it.
Okay. Chapter 13. Let's put this down. Homework week 1, chapter 13. Which question?
Let me see. It's like 13.3.
13.3. Okay, stereochemistry. Let's see if I can share this screen. Let's see, where is it? All right, let me see. I'm going to stop sharing here. I'm going to start sharing organic chemistry 2 top hat. Let's do that. Okay. Can you see my screen now?
Yes, I can.
Okay. So right here we have a really good thing to do. And we're starting to, let's start with what we know. All right, ignoring stereochemistry, so that's great. We have a 1-to-1 reaction of bromine and 1,3-cyclohexadiene at 25 degrees in the dark. Okay, so the first thing we do is we draw cyclohexadiene, okay? Now, the first thing we see when we draw cyclohexadiene is it's a conjugated diene, okay? So that tells us right away that when we add something to it, we have an opportunity for a 1-2 addition or a 1,4 addition, okay? Now, we also noted it's bromine, okay? We're doing with reaction with bromine, which means we're gonna add a total of 2 bromines to the system. One on the 1 position and then one on the 2 or the 4 position, because those are the possible options here. Okay. The fact that it's in the dark and in the absence of peroxides means we're not gonna do a non-1,4, 1,2 addition. So, and at 25 degrees means we're not gonna over-brominate that. And we only are gonna have 1 equivalent. So, that being said, if we draw a cyclohexadiene right here, and we did a 1,2 addition across it, we're gonna end up with the 2 bromines on the 1 and 2 position, like here in number 2, okay? Now, if we took a, okay, so it can't be this one here because we don't have 2 bromines on our system. So we can eliminate part 3. If we look at this one right here, this is adding 1, 2, but our double bond is in between the 2 bromines. I don't think any of our addition products showed us where we had the double bond staying in between here. So this is our 1, 2 addition right here. And then this would be our 1, 4 addition. So at this reaction, we're going to get a mixture of the 2. So I think our answer is E, both 1 and 2. Okay. So again, the attack mechanism is draw down what you're starting with, because if this is where I get to test your nomenclature without testing your nomenclature, because you have to draw it out and say, okay, my reaction is going to be a 1, 2 or 1, 4 addition. What would those products be? Now I look for those products. Okay?
Yeah, thank you.
So that's how you would attack them like that. And then, so this is an example of where we're going to go, okay, this is kind of the same rule. We want to do figure out where we're going from here. Okay, we have a cyclohexene, right? It's a conjugated cyclohexene. And so if we're going to do some kind of substitute over here, we only want 1 halogen on that system. So that means we can't add bromine, because that's going to add 2 halogens to our system. So that means we've got to have at least B or C here, because we want to add a hydrogen to a 1 and a 2, or a 1 and the 2 position, and then we want to, actually, because we want this group here, we'll probably want it in a 1, 4 addition. So we want it heated. So it's heated, that's good. So now we'll have a halogen and a double bond on this reaction. So if we react it with this reagent, that could work there. That would actually generate the product here. But if we have the halogen now on our cyclohexane right here, and we made a Grignard out of it, and then, so that could be a nucleophile. However, at the end, we're adding an alcohol right here. The alcohol has a proton on it. So that's just going to quench your Grignard reaction, giving you the cyclohexene. So number C won't give us a choice. A won't give us a choice. That eliminates these other 2, so it has to be B. Okay? See how you can down select from what you know, and at least draw each intermediate in the system, and that gives you what can happen next. Okay?
For that homework question, it told me the right answer was C. But I'm trying to double check to make sure that ours match up. Yeah, it told me it is C.
Wow, it's wrong. It's B. That is wrong. It can't work because this is an alcohol. It would quench the reaction.
Yeah, I was.
Okay. Edit without unassigning. I'm going to fix that right now because that is wrong. Edit. No, it's B. There we go. So now it should be right. Let me double check, make sure it corrected it. Correct answer is that. Okay, that's right. And okay, there we go. Now it's right. Thank you for catching that.
Yeah, because I was kind of confused about that one. I was like, that alcohol and like protonating it.
Yeah, because you would generate your Grignard reaction. You would have 1 halogen. You would generate your Grignard reaction, and then this would just quench the reaction out of hydrogen.
Okay. Okay, yeah, gotcha.
We'll probably have to run a grade report on this one again then. You got it right. You can actually see what the general, a lot of people are getting the nerve right. So this actually tells me how many responsive I got on each of the different possibles. let me see how many people actually, okay. Most people got that right, and most people got that right. So, yeah. So, okay. Okay, I'm going to stop sharing. Are there any other questions before we head on out? It's a little past time, so your time is valuable. I'm going to go ahead and stop recording.